Okay guys, as I promised, we are going to look at geometry today, and as I mentioned before, it is the biggest topic in maths. Spending, here's the exam guidelines I wrote for SACAI, and you'll see there that and this is not exactly how your paper is. Question 1 is in statistic, question 2 analytic, question 3 trig, but this is roughly the first few questions is stats. The next section is analytics and then trig. And notice that geometry, trigonometry, and analytic geometry, they span so far the biggest part of your grade. They count 45 marks. Okay, each out of 300 really, because your paper 2 is 150. And paper 1 is 150. So, and they two together count for a mark out of 300, which becomes your percentage, which divided by 3 becomes your percentage. Make sense? So you can see for geometry, trig, and analytic geometry, they take up the biggest portion of your exam, which I don't think is fair. I must be 100% honest with you. I think you spend so little time on geometry in school compared to how much it actually counts in the exam, and that I'm actually pushing that they change. I don't know if I've got that ability, but anyway, this is what it's going to be like for you guys. So in geometry, in this document I gave you all the proofs that you need to know. Okay, so there's the proofs. There's not a lot of proofs. You can see 1, 2, 3, 4, 5, 6. Okay, but you can be sure you'll have 1 or 2 of those proofs in the final exam, each one counting 5 or 6 marks, which, I mean, that's almost 10% if they ask you 2, and yet in the prelims no one got the single proof for equiangular triangles are similar, correct? So we'll look at the proofs today. I'll look at the circle proofs that we need to know. And then down here I also show you, if you go down, what should you be able to do in Euclidean geometry. The likely format is that they ask you a proof from the grade 11 theorems. Now that's the circle theorems. So it's likely that they'll ask one of them and one of the grade 12 theorems, which is the triangle theorems, similarity. Okay, at least one question will be about finding unknown values using your grade 11 theorems. So the next very important thing is that you need to know your theorems. If you don't know your theorems, you're screwed. They're not on a formula sheet somewhere. You need to know your theorems off by heart. You need to understand what they mean, how they apply, and have practiced using them. At least one question proving certain relationships. So in other words, one question would be, they give you literally an angle 34 degrees in a sketch, and then they ask you find certain other angles in that sketch. Another one would be proving relationships. So they tell you, prove that this angle is equal to that angle, or this side length is equal to that side length. So there'll probably be a question where they give you values, but then there will be a question where there's no values, and you have to show that this angle is equal to that angle. Likely to be a grade 12 proof. At least one question where you have to find unknown values. If I say values, it means values like 2, 3. So you probably have to find a side length using your grade 12 theorems. Grade 12 theorems has got to do with similarity. So similarity has got to do with side lengths. So while the grade 11 theorems have got to do with angles. In circles, we've got our angles on a chord is equal, things like that. At least one question would be about proving relationships using the grade 11 and 12 theorems, and then at least one question for finding lengths and proving relationships using similarity or proportionality. Okay, proofs to know. Here's the proofs that you have to know. Okay, I just repeat them there again. All proofs. These proofs have, for all the proofs, you get 1 mark for the construction. So you have to indicate on your sketch, you get an answer book. you have to show the construction, or at least write down construct line blah blah blah. Okay, so I'll show you now some of the proofs. Just so you know, I don't remember the proofs. I remember the construction. That's all you have to remember. If you know the construction, you can figure out what you have to do from there. So I'll show you some examples. Then there's abbreviated statements when in geometry we make a statement. For example, I say angle this is equal to angle that. I must give a reason why I say that. And these are some abbreviations for certain reasons you can give. Okay, a lot. Okay, this is a formula sheet. This is not the formula sheet that you will get. This is a formula sheet I suggest they give. Because the one you guys get just gives you way too much nonsense. You don't use all of that. You go get Tn is equal to A plus n minus 1d on there, or so that those formulas you have to know. But these are more formulas that I suggest. If there's any ones you don't study off by heart, let it be these ones. If it's not here, don't study it off by heart. Okay. So use this as a guide, and so in other words, this formula sheet is what I suggest you don't have to know off by heart. It's ones that I suggest they give you. But the rest, it would be to your benefit if you actually know them off by heart. Okay. The reason why is because if I know a formula off by heart, I can recognize it in a problem. But if I have to go to a formula sheet, for example, if I do the present value of an annuity, I get to the question and I know now I have to use a present value of an annuity. So then you can go to the formula sheet and get that. But sometimes they give you a structure and you have to use the reverse of the formula. So you know P, I need the formula for P, so you go read it off P. But what if they give you this side? You don't know this side, so you don't recognize that it is P. But if you know that structure, that formula, you'll recognize that this is present value or whatever. Okay, so that's my suggestion on how to use this exam guidelines. You can go see. I tell you literally in every paper what topics there are. Algebra, the majority of question is based on grade 11 work. Okay, which involves solving equations, things like that. Grade 12 we don't do very little of that really. Functions and graphs, then for example I tell you what is the most important things and what most common things that you'll encounter in the final exam when it comes to these topics. Okay, so make sure that you actually go there and tick, okay, quadratic equations, I know how to solve it using factorizing. I know how to solve it using the quadratic formula, most people do. Exponential equations, especially requiring factorization. Do I know how to solve an exponential equation? Do I know what is an exponential equation? If you don't, then highlight that and go and study it. If you don't know, come and ask me. What the heck is an exponential equation that requires factoring?
So where's this bit?
It was an announcement just before your before your prelim exams. I sent it 17th of September. I think before paper 2. No? Before paper 1 was better. Okay. So go and find it there. Cool, so let's get into the geometry. Okay, where's my spot? Okay, I'm going to try and remember as many of the formulas of the theorems as I can off my mind, and that's what I suggest you do. I suggest you go and try and recall. There's many. I mean, there's probably 40 theorems in total. and you should be able to recall them from the most basic ones you can think of. You should go and try and recall it. So let's think of one of the most basic things you know about geometry. What's one of the most basic things you know about geometry? Basic. What do you know? Yeah. Who's
all angles of a triangle end up to 180 degrees.
Okay, very good. So he says that if we had a triangle, this is it. You're telling me that if we had a triangle, all the angles of the triangle add up to 180 degrees. Is that fine? Okay. Why? Why is that true? Didn't actually go down. Like, you're right. Why on earth do we assume that? How on earth can we be so arrogant to think that that is just true? Don't you think it's a bit arrogant to just think that is true? I can actually give an example where it's not true. You know the example. You heard it. If you go and stand on the North Pole and you head down to the equator, what angle do you make when you reach the equator?
Isn't that 90 degrees?
So here's the Earth. If I'm at the North Pole, I'm heading to the equator. I'm drawing a straight line, isn't it? I'm drawing a straight line and I'm making a 90-degree angle. If I go back to where I started and I make another 90-degree angle, and I do it the same again, at what angle will I reach? 90 degrees. But I made a 90 degrees angle there.
Yeah.
So I've actually drawn a triangle whose inside is 270 degrees. So this is not always true. It's always true based on an assumption. And that's the thing about trigonometry. It's not that you're going to use it ever in your life. Maybe. But that's not what we're trying to teach you. We're trying to teach you to reason, to think. So if I make a statement, what is that statement assuming? And if I now go and test that assumption, I want to see, well, how do I know the thing that I'm assuming is true? Now, in order to go and know something is true, I need to prove it. Okay, let me show you the proof. And then you tell me, in this proof, what did I assume? In this proof, what did I assume? Here's my proof. My construction is, so here's my triangle. I'll show you the proof. This is one of my favorite proofs. The proof is, here's triangle ABC. The proof is that, is this angle, I'm going to draw a line line DE. That's my construction. I'm not going to write everything out nice formally, okay, because this is, I wouldn't say primary school stuff, it's not primary, this is varsity stuff actually. But it's simple enough so you guys can understand it. You never do it at school. Do the proof, which is, I think, one of the problems why students struggle with geometry. Because it's very reasonable. You can really understand it, and it's when I did geometry in my third year. At varsity, I struggled doing well. At school, I did very well, but at varsity, I struggled getting. I got one distinction up to into my second year, and when I did geometry in my third year, since then I've never not gotten a distinction because it taught me how to reason, how to think, and now I know I can understand anything. That's why I love physics and chemistry now, because I can figure it out. It must make sense. Okay, so in this proof, I want to prove that these three angles together make 180. So I draw line DE parallel to line BC. Now, if these two lines are parallel, what can you tell me?
Equal gradients.
Sorry?
The equal gradients.
No, that's analytic geometry. So we don't use any gradient or distance formulas or anything like that because that requires x and y. This is true anywhere on any space, on any surface, whether in the Cartesian plane or not. Okay. No, this.
B is equal to A1.
So there's three angles. You are saying that A1 and B, those are equal. Why?
Alternate angles.
Alternate angles. Okay, so A1 is equal to angle B, alternate angles. Okay, so do you see now you're giving some reasons, okay? Now you say what you're trying to prove, so to prove is you're trying to prove that A plus B plus C is equal to 180 degrees. Okay? We know there's some exceptions. We'll look at why do those exceptions occur, but we want to prove this at least for this situation. Now, what does this mean? Okay, we'll get to that just now. You'll see, it will explain why I made my construction. Okay, so we know these two are equal. What else do we know? What else can you tell me? So A3 and C, for the same reason. A3 is equal to C, also alternate angles. Whenever you use alternate angles only apply where? Parallel lines. So then you have to show, you say alternate angles and people say, well, they ask you, why are you using alternate angles? Explain. So you'll say, I'm using alternate angles because DE is parallel to BC. I'm using let me write it out. I'm using alternate angles because DE is parallel to BC. Okay, who can, that's the proof almost.
Common angle A2.
Okay, so common angle A2, yeah. What's your point?
Angle A, the whole of A is equal to 180.
In other words, so A1 plus A2 plus A3 is equal to 180 degrees. And since A1 is equal to B, so you're just replacing now and A2 is just equal to A, and A3 is just equal to C. There we've proven that angle A plus B plus C is 180 degrees. See, very simple proof. Okay? But you use two reasons in this. Well, three reasons really. No, two reasons. Two reasons. So for example, why is A1 plus A2 plus A3 equal to 180 degrees? It's angles on a straight line. Angles on SDR. So these shorthand, these abbreviations, don't go and study them, guys. Like I know that there's teachers that will kill me for saying that, but that's not the idea, is that you know a bunch of shorthand. It's that you can communicate your reason, wow, in a quick way. So angles on SDR, I don't even know how to do it. SDR, GHT, whatever. Might as well read them straight line. Angles on straight line. Okay, so notice how we've used two things. We've assumed these things are true in order to make this proof. Okay, so one of the things we assume is that the angles on a straight line is 180 degrees. It's not really something we assume. It's something we define. In other words, we define a rotation. A rotation is defined as 360 degrees. Now when I define something, I'm just giving it a value. Like I could have said a rotation is 720. It's choosing anything. I mean, it's just a value. It's just like I say, for example, in physics we say Avogadro's constant is 6,23. It's just a name we give to a size. This is just the other way around. We give a size to a certain thing, and if I talk about half that size, which is now a straight line, isn't it? That's 180 degrees. So I don't need to prove that angles on a straight line is 180. That's just what I say. That's what angle sizes are. A straight line is 180. We give it that definition. Does that make sense? So this one is fine. Okay, this is just defined, and that is why if we said angles on a straight line, if we defined a rotation as, let's say we made it easy and we said a rotation is 1,000 degrees, then what will the angles add up to inside a triangle? 500. Because that would have been the way we defined it. But we define it as 360. I don't know why. Good question. Why it would be, but yeah, seems to be some multiple of 6 and something to do with it. Nevertheless, the other thing we assume is that alternate angles are equal, and that is why that is the difference between this triangle and that triangle here. On this Earth's surface as a sphere, alternate angles are not equal. Now, before we can go and see why, we now need to go and look at alternate angles and see, well, do you understand? That's even a more basic principle than the angles inside a triangle, because I use that principle to prove angles inside a triangle is 180, which makes alternate angles even a more basic theory. Okay, so let's go and look at parallel lines. First of all, if I wanted to prove that alternate angles are equal, here's my alternate angles. Okay, I want to, my parallel lines, A, B, B, C. Now I want to prove that alternate, A, B, C, C, D. Now I also need to number those points there and there. And let's say I want to show that angle N1 is equal to angle M1. Okay? Now, in order to do that, there's no construction in this case. Okay? There is another assumption. And this assumption cannot be proven. It has to be assumed. Now, the moment you assume, okay, all assumptions are assumed, but if I can prove an assumption, it's a theorem. If I can't prove an assumption, then it's an axiom. So an axiom is something I believe. I just accept it's true. I can't prove it. I have to accept it, and intuitively, it feels right. But there can be examples of exceptions. And the assumption here is that if I have two parallel lines and another line intersects them, then the angles between the parallel lines on the same side of that intersection line. So the angle between on the same side, that's those two angles. You understand what I mean? The angle between the but on the same side. So not one angle on this side and another angle on that side. Do you understand what I mean? So that's the angle between the parallel lines on the same side are supplementary. Supplementary is just the word we give to, they add up to angles on a straight line.
So would that be the same for the other side of the...
And for this side, same thing. So these two angles are supplementary because the assumption is between this line on the same side. Now that's why on Earth, on the Earth's, even before I get there, notice that in this assumption, okay, we say we have parallel lines. We have an intersection, an intersecting line, intersection, and now we've got angles. Now we've already defined what angles are. Angles are when two lines cut each other. All of those angles should add up to 180 degrees on a straight line, altogether to 360. But you notice that in order to understand the assumption, we have to first understand what do we mean by parallel lines. What do you might mean with parallel lines?
Parallel lines.
So it's a definition. It's something that we need to define.
They'll never come toward each other. Internal quality will always stay in
the same distance apart.
Yeah, they'll never.
That is not really the definition of parallel lines, but it is a conclusion because this is true. Because we assume this, it's true that they never come, because we assume that these two add up to 180. That's why these two never come together. But look on Earth, the real definition of parallel lines they are lines that have no point in common. In other words, a point that two lines have in common is the point where they cut. It's exactly what we were doing on that graph. Okay? The solution to a simultaneous equation is where the two graphs meet each other. It's a point that they have in common. Parallel lines are lines that have no points in common. Okay? That's the definition. Which means on Earth, I can draw one line here on Earth. Any line that I draw on the Earth's surface, if it's a straight line, will meet up on the other side if I make a straight line. So it will always be a circle. But look here, I can draw another line that goes like that. You see, they never cut each other. The one goes around the equator, the other one is a little skew on top. And notice now if I draw any other line that intersects them, both, these two angles are both more than 90 degrees. So they will add up to more than 180 degrees. These two on this side, both of those angles are less than 90 degrees, so they'll add up to less than 90 degrees. You see, so the moment I make this assumption, what I'm actually doing is I'm assuming my surface is flat. The moment I assume that, I'm creating a universe for my maths. And my universe assumes now a flat universe. Now, the maths will work on paper, on small surfaces, because if you look at the Earth, appears to be flat. So, approximately, it will work out on the surfaces that we work with in general. But as soon as I go to a larger scale, so for example, if I had to do a triangle between here and the furthest galaxy that we can observe, then it might look flat, but it's not. Okay, it actually curves. Space curves. Okay, so but that's an assumption that works on paper and on small scale. Now, let's say we do assume this. How can we then prove that the other? So this is assumption. It's called Euclid's postulate. Okay, and you don't need to know that, but it's interesting. So if I had to prove now that the alternate angles are equal, in other words, if I know that M2, so I'm assuming that M2 plus M1 is equal to 180 degrees. Can you guys give me a way of proving, so to prove that M1 plus M1 is equal to M1? How could we do that? Using some of the things we already now know. I know
so if N1 and N2 are equal to 180, meaning if you use the same thing.
Yeah. So in other words, N1 plus N2 is equal to 180 degrees.
And M1 is equal to N2. It means that.
Wait, this is what we want to prove, so we can't use it.
Oh, we can't use it.
Well, this is the result. So whenever they ask you prove something, you can't use it. That is your result. That's what you want to get to. But you're on the right track. I know this is 180. I know this is 180. How can I use these two? If they're true together, why is this true?
M1 plus M2 is also equal to 180.
N1?
M1.
Yeah, but you can do it from here already. You don't need to also do it down here for that. Just using these two facts, the two with the tick marks, I can already prove that N1 is equal to N1. How?
Alternate angle.
No, that's what I want to prove.
That's what you want to prove.
Yeah, I want to prove alternate angles are equal. Because I assumed it to prove that triangles in a straight angles in a triangle add up to 180, and so that's just how you should think. Just assume things are true and let's prove it. There's not even any construction with it. Just these two things. Look, guys, you want to prove that N1 is equal to M1. So use this formula and maths. Use that M1 is then equal to 180 degrees minus N2. And from this one, N1 is equal to 180 degrees minus N2. Now look, I use the same formula to get both answers. Doesn't that mean that N1 is equal to N2? Can you make this, if these two things are true, if this is true and this is true, can you see why this is true? Can you see that? Luisa? Do you understand what I'm doing here?
Yeah, but if you've got N2 on both sides, does that mean that N1 is equal to 90 degrees?
Where do you have N2 on both sides? You don't have N2 on both sides.
The M1 equals 180 minus N2 and the N1 equals 180 minus N2.
Yeah, but they're not one equation.
Oh, okay.
They're two different equations. So I'm basically saying that if you take my wallet and you double my money, you get an answer. If we take your wallet and you double your money, okay, we get the same answer. Doesn't that mean you and I have the same amount of money in our wallet? We use the same formula. The same formula gives the answer for the wallet, the money in your wallet, as it gives for the wallet, money in my wallet. So it must mean that the money in our wallets must be the same. Does it make sense? Okay, now this is actually called, this is also an assumption. Why do we assume that? If I say A is equal to B, and I say but B is equal to C, would you say that A is equal to C? If B is 10, then A is 10, then C must also be 10. But that's actually an assumption. It's something you assume that if A is equal to B and B is equal to C, then it's called the law of excluding the middle, because if I say A is equal to B and B is equal to C, then I'm saying A is equal to C. I'm excluding the middle. It's a law of logic. It's something we can't prove. We have to assume it. But it's intuitive. Do you understand? It's not that I feel like I'm taking some massive leap in logic. But and there's three laws of logic. The first law is the law of identity, that A is equal to A. Something is equal to itself. Okay, 10 is equal to 10. The second is the law of non-contradiction. So A is not equal to, and this is the sign. Well, you get different signs for not, but A is not equal to not A. In other words, something can't be true and false at the same time. Okay, 10 can't be not 10. Do you understand? If something is what it is, then it is what it is. It's not what it is not. See, again, we can't prove it, but it's assumed. Okay. Now, therefore, if I can show, and it's just a way of proving sometimes. Like it seems trivial now, like that's stupid, but. For example, let me give you an example why this law of non-contradiction is vital. we use it in our very first proof in geometry. In geometry, we start with 3 assumptions. The one assumption is that on a straight line, there exists at least one point. We can't prove it. A line is not defined as a bunch of points, and a lot of people define it like that. But you can't define. I'm not going to go into that now. But on a straight line, there's at least one point. Okay. The second assumption is that between any 2 points exists one unique line. This is Euclidean geometry. Now, on Earth, that's not true, because if I draw, so in other words, if I had 2 points, there's only one way of drawing a straight line through those 2 points. I can only draw one straight line through those 2 points. But on Earth, if there's a point and there's a point, I can draw a straight line going this way through those 2 points, or I can draw. Okay, wait. Let's say the 2 points. One is on this side and one is on that side of the Earth. Then I can draw a straight line like this through them, or I can draw a straight line like this through them. You understand? Now there's many. So on Earth, these are the assumptions for Euclidean geometry. It's the assumptions we make, and it produces a flat universe, and that works on paper and on small scale. But as soon as we go beyond that, we need to change our assumptions to include for a curvature. Okay. The third one is that so far we haven't said anything exists. We just said if they exist. For example, if there's a straight line, there's a point. If there's 2 points, there's at least one straight line. So the third one is there exists at least 3 points. So these are the 3 things we assume, and then we prove about 20 theorems, and then we can't prove anymore. Then we assume Euclid's postulate, and then we can go on and prove triangles. Now, I'm not going to go into all of that. That's literally 3rd year geometry. It's not complex. It's really actually very simple. And it really helps you to understand what are we actually doing later on. Okay, but the first theorem that we prove is you must prove, so then they go and define what is a parallel line. A parallel line or parallel lines are 2 points that have no points in common. So now they say prove that lines intersect in one unique point. So in other words, they say if I had 2 lines that cut each other, prove that 2 lines can cut each other only once. That's the point. If I had 2 lines that cut each other, I must prove that they can cut each other only once, only using these 3 assumptions. And so these 3 assumptions and the laws of logic. So we start by saying, okay, well, let's prove it's true. Let's assume it's true. Assume line AB and DC meet in 2 points. A point M and N. Then M is on AB and DC, because we say when 2 lines meet, it's a point that's on both of those lines, isn't it? So if they meet in 2 points, then M is on AB and CB, N is on A, B, and D, C. Therefore, there exists 2 points. There exist 2 lines through 2 points. And that has contradicted our assumption between any 2 points exists 1 unique line. You see, we come to a contradiction. So this can't be true and this true at the same time. So in other words, A cannot be not A. Do you see? But we have to assume this is true in order to now go on and assume. Therefore, one of these 2, we made 2 assumptions. We either assume that there cannot be 2 points through 1 line, or there is only 1 line through 2 points, or we assumed that there are 2 lines that cut in, that there are 2 points where 2 lines cut. So one of those assumptions must be wrong, and it must be this wrong. So if we deny this one, then its opposite must be true. If this one is not true, then there are not 2 points where 2 lines intersect, which means there can only be 1 or no point. If there's 1 point, then we've proved it. If there's no point, then they're parallel lines. And we said these aren't parallel lines because we are talking about lines that intersect. Do you understand like kind of how this reasoning go? So one of the most basic theorems are actually the following. First of all, just when it comes to angles, we first of all just define the size of angles. And we define a rotation or a revolution. Is it a revolution?
Yeah, revolution.
A rotation or a revolution. A revolution as 360 degrees. That's just how we define it. And so half a revolution or half a rotation is then what we get on a straight line, and that would be called supplementary. Supplementary is 180 degrees. Okay? And then half of that, okay, so in other words, what a supplementary angle is when 2 angles add up to 360. They are, each angle is 100, is supplementary. On a perpendicular angle is defined as when 2 angles are equal, perpendicular, equal supplementary angles. Supplementary angles. In other words, there are 2 angles that are equal and they add up to 180 degrees. Now, there's only one way that's possible. If angle x plus angle x adds up to 180, so they're 2 equal angles, that means that so perpendicular angles are 90 degrees. Okay? So perpendicular angles are defined, they're not defined. Perpendicular isn't a 90-degree angle. Perpendicular is an angle that is equal to the angle next to it, and they both add up to 180 degrees. But that then follows that both must be 90 degrees. Okay, so these are some of the basics. Now the next thing that we get to is opposite angles. Is it opposite angles? I forget the name. How about you guys try proving for me that angle, the things that we've now talked about. Can you prove to me that angle A1 is equal to angle A2? Let me do this. A2, 3, 4. Okay. Let me just get the right wording here. This is, it's not opposite angles. vertically opposite angles. Vertically opposite angles. Okay. Can you prove from you? Sorry?
A1 is equal to A2.
Sorry, in this case now A3 because I changed the numbers. And when we talk about angles, we just use that little cap.
A1 plus A2 is equal to 180.
Okay, so A1. So let's just skip it a little bit. Let's just say A1 is equal to 180 degrees minus A2. So in other words, I define the angle that I want to prove in a formula, and I'm hoping to define the other one with the same formula. Okay, why? Why is this true?
Supplement, no, it could be supplementary.
It's actually angles on straight lines. So it really have to go and prove that angles on a straight line is 180 degrees, but I'm not going to go angles on a straight line. Okay. Okay, next.
A3 plus A4 is equal to 180.
No.
Okay, A3 is equal to 180 minus A2.
Minus A2 as well. Yeah. So we'll use this fact. These two together gives me 180. These two together gives me 180. And since I'm using the same angle for both to get to 180, and there it goes. That is law of excluding the middle. If this is equal to that, this is equal to the same thing, it means they must be equal to each other. A1 is equal to A3. Yes. Okay, so that is, I just want to get you guys into the spirit of proofs and how you can see I write down, and I'm supposed to write down this here, and this one you can write down because the laws of logic, we don't have to go and give them reason. We don't go and say now, yeah, the law of excluding the middle. We assume that people reading our proofs know the laws of logic. If you can show them, and this also basic algebra, like if x plus y is equal to c, if that's the theorem, and you just go and say x is equal to c minus y, well, it's just a different way of stating the same theorem, just because you used a little bit of algebra. Okay, so save yourself some time and skip that. So for example, when I use the fact that the interior of a triangle adds up to 180, I don't go and say a plus b plus c. It depends on what am I trying to do. If I want to somehow get an expression for a, then I say a is 180 degrees minus b minus c. And I give my reason, interior adds up to 180. And I expect the person reading that they are understanding where I'm getting this from. And you don't get marks in the proofs for your simplification because it's grade 2 simplification. Okay, not really. Grade 6, 7, 8 maybe. Okay, simplifications. Okay, you guys get the idea. Okay, so now we've proven the vertically opposite angles are equal. We've looked at why alternate angles are equal. Okay, these guys are probably the most important theorems that you can know. Vertically opposite, and those are theorems that precede actual theorems that you do in grade 12, 11 and 12. Then there's another one that's parallel lines, and they are called corresponding angles. You can see why these are called alternating angles, because they are on alternating sides of your cutting line. These are called co-interior angles. Remember what Euclid's postulate was? Is they're on the inside of the parallel lines, and they're on the same side of the, so they are co, which means on the same side, co means together, and interior means inside. Okay, so that's why we call them co-interior. These are called, sorry, the green one that I showed you was alternate, and you can see why they're alternating the sides, and usually alternate we spot with looking for a Z. Yeah, because it's those little insides of the Z. And then co-interior we look for a U, for the inside of the U. And then this one is called the corresponding. Let me show you why we call it a corresponding angle. Okay, so notice my parallel lines there, and we are saying that this is a corresponding angle to that one. Let me rather do it like this. That one corresponds. That one corresponds. I just need to do something if you won't see that. This one corresponds to this one. The red one corresponds to that one. The pink one corresponds to that one. And the green one corresponds to this one. Look quickly why. Because if I were to move this bottom one up, they would correspond. You see? So that's why we call it a corresponding angle, because they correspond. Okay, cool. Corresponding, we recognize, do you see the F? So for example, is those two correspond. So I know our teacher, there's very little I appreciated that my teacher taught me in school, because she taught me wrong, but on a lot of things. But she did teach me this that was useful. If I had to find out, I'm sure you saw it somewhere. But so the F, the U, and the N or the Z, to look for that when you have parallel lines. Again, if they don't give you parallel lines, and a lot of people use that, they would get a circle like that, and then actually let's do it like this, something like this, and they would say that is corresponding angles there. But yeah, you can see the Z, but that's a zonky Z, because they don't tell you these are parallel. If they don't tell you they're parallel, they're not. Okay, you cannot assume it unless you've proven it in a previous question that they are parallel. So let's say you've proven that this angle is equal to that angle. Then you can say, as a conclusion, that means that these two are parallel. So you're using the inverse of your the theorem that we've now proven. We've proven that when lines are parallel, alternate angles are equal. Now, that means if alternate angles are equal, lines must be parallel. And it doesn't really just follow naturally, we actually have to prove it as well. And that's then called the converse theorem, when you're using your theorem backwards. So, for example, if you use the fact that two angles are equal like this, and they're made by two lines that don't intersect, and those two lines are cut by another line, and that line that cuts them, their alternate angles are equal, you can assume that the lines are parallel. Not really assume, you're applying the theorem that hopefully you've proven it so that you can have confidence in that. Okay, so these are some of the most basic fundamental ones, and then comes the one that we've now already proven, the one that you guys seem to know before you can spell your name, that the interior of a triangle adds up to 180 degrees. You can see again, it only works because alternate angles are equal. If it wasn't for alternate angles, it's actually not the alternate angles thing, it's the interior, co-interior theorem that we assumed. And as a result, the alternate angles theorem is true, and therefore interior angles of a triangle add up to 180. Okay, so that's another fundamental one. Then there's another one that's very, very, very important, very often used even in grade 12, and that is that the exterior angle of a triangle, this angle here, so here's A, 1 and 2. So exterior angle means I have a polygon. A polygon is a shape made up of straight lines. So I have a polygon, and one of the sides of the polygon has been extended. The angle that makes with the polygon, in this case a triangle, so let me stop using the word polygon. So if I have a triangle and I extend one of the sides, the exterior angle is the angle that extended side makes with the triangle. Okay, that angle is equal to the sum of the opposite interiors. So that angle A2 is equal to the sum of the opposite interiors. Can you prove it for me?
A plus B plus C is equals to, yeah. A plus B plus A1 is equals to 180.
Okay, so do it the way I suggested. Yes, you're right.
A1 is equals to 180 minus...
Yes, A1 is equal to 180 degrees minus
B.
Minus B. Let's do it like this. Minus B. Sorry. Minus B plus C. You understand why I did it like that? Okay, so it's minus B minus C, but I just group them together. Minus B plus C.
A2 is equals to 180.
That's fine.
180 minus A1. It's correct, but...
That's okay. Now you've got an expression for A1. So you can replace it in here. Simultaneous equations. So in other words, A2 is equal to 180 degrees minus 180 degrees minus B plus C. So 180 minus 180 is 0. Minus times minus is a plus, so it's B plus C. Okay, this was maybe not the best way to have done it, but you would have figured it out. Do you understand? Can you see how this works? Is you recognize this in-between relationship that and again, when I make this statement, I must give a reason. And interior angles of triangle. This one, angles on straight line. Okay, and these are the two things that your proof relies on. Okay. Okay, so I can't think of another important common foundational theorem. There's now a bunch of congruency theorems that we get to, which is now a new type of topic. Congruence is when two things are equal. It means equal. But the problem with equal is that if I were to measure two of you and your height, and you get the same height, I wouldn't say that you two are equal. I would rather say your height is congruent so it's not difficult. Equal would mean it's the same thing. So 10, so for example, if I say A is equal to 10 and B is equal to 10, then A is equal to B. It would mean that they are the same thing. They're both 10. But because when we work with in geometry with shapes, when I have two different shapes, they can't be equal. They're not the same thing, but they are the same in size, for example, and shape. So if something is the same size and shape as another thing, it's congruent. So for example, if I have a line here, it's called a segment. A line is actually strictly defined as something that goes infinity on. A ray is something that has a start, but it never has a finish. And a line is actually something that never has an ending. So that's it. This is called a segment, a ray, and a line, but that's not for the way that they do geometry in South Africa. Nevertheless, or at a high school level in South Africa, if I have a segment in length the same as another segment, so let's say this is AB and this is BC, then AB equal to BC would mean it's the same line. It's not the same line. It is congruent to BC. It has the same length. Do you understand? So if I had a triangle here, now it's okay if you, when you refer to length and you just say AB is equal to BC, that's okay. But technically speaking, if this was the same length as that, if this was A, B, C, D, and this was the same length than that, the only two lines that I can compare, that I can say is equal, is AC is equal to AC. Because it's the same line. AB technically is congruent to AB. It means the same in size and shape. Now, shape lines don't have shape, if they have maybe direction. That's not what we mean. Shape just means the. Yeah. So some of the congruency rules then come down to, and I'm not going to look at all the proofs, but if I had two triangles, okay, and congruency rules are very, very important. So if I had two triangles and they are congruent, if A, B, C is equal to D, E, F, if A, B, C is congruent to D, E, F, it means A, B is congruent to D, E. So the same portion of it. AC is congruent to DF, and BC, or let's say I called it CB, then I must say is congruent to FD. Understand? Okay. Do you get what I mean by congruency? Now, there are certain theorems that now, so this is the condition for congruency, and this would be, if I can show that all three sides are equal, then there's a bunch of theorems that follow before this, that when sides of a triangle are equal, the angles will also be equal. But we won't go into that. But if I can show that three sides are equal, then I've shown that they are congruent. I've shown that they are. So the next thing I can do is, if I can show that two of the sides, so if all the sides are equal, then it will follow that all of the angles will also be equal. It doesn't work the other way around. Just because angles are equal doesn't mean sides are equal. Let me give you an example. Here's a triangle, and here's a triangle. They've got, if these two are parallel, they've got the same common angle. Here's the F, do you see the F? So there's corresponding angles there, and they've got corresponding angles there. So just because angles are the same, doesn't mean they're side. You can obviously see they've got different side lengths. This side length and that one is obviously not the same. Same for all the others. Okay. These are called similar triangles. So similar triangles have equal angles. Congruent triangles are similar triangles. Similar triangles are not necessarily congruent. They could be. Okay. So if I can show, and I really do want to, but we don't have enough time. I love going through the proofs. But if I wanted to show that two triangles are congruent, then I can either show that they have all their sides are equal, or I can show that two of the sides are equal and an interior angle. In other words, the specific reason that I would give in the end is they are congruent because they have a side, an angle, and another side. Now, the reason why it can't be these two, and now it won't work in the video, but if I only had these two sides, that are equal. Okay. Notice that if that angle, notice now the opposite side. Yeah, is now given by. I'm actually giving you. I don't think it's going to be long enough to. Okay, so let's just use a part of that. For this size to be fixed, I will have so assume. Yeah, actually, let's use these two as the given ones. I've proven that these two are equal, okay? And I know that that angle is equal. Then these, if I go and measure this, that would be a fixed size, okay? The moment this angle starts changing, then I'll have a fixed size. As long as these two stay fixed, this one can't have another choice but to be that size. Does that make sense? So that's why if I can show two sides. Okay, but it's not true for this third side, because it feels like it should be true though. An angle on two sides. Is it two? Yeah. It feels though to me that if I take another angle, I'm given another angle, is true. Other than the interior angle. Why? Oh, because this angle is not fixed. So let's say I had this angle, okay, up here, but these two, this angle is not fixed. He can move. Okay, that angle can move. This angle can't move. Okay, look at, so this is a fixed angle up here. But this one can move as much as he wants to. Then I could have that one, okay, this one is also fixed. And I think the problem is not, let's take at that angle, okay. I don't think this thing is long enough. Let's try it like this. There could be two angles that work. There could be an angle at this point, do you see? Because this one is fixed, that one is fixed, and this angle is. Okay. Then there's an angle that works here, and there's another angle that works there. You see, there's two options that this one can have. It's not infinitely many, but there's two options. So that would be why it can't be interior. So let's see if I can draw it. Okay, so for example, if I move this one, so these two are the two sides I know, and I'm also given another angle, for example, that angle. Okay, then there could be another one where the angle between, now I'm going off my page, okay, but the angle there, these two angles could have the same while I'm still using the same lengths. This length and that length is the same, and yet they're not the same shape. This length is equal to itself. Okay, so but let's not go into that. So those are two options. I could have, well, let's look at all the options. I could have all three sides or all three angles. All three sides will always work. I could have all three angles, not sufficient. Okay, I could have two sides and an angle, so one of the angles, and the only time I can do that is if I replace the middle angle. Next is I could have a side and two angles. Okay, and that will always work. Doesn't matter in which order they are. Okay, and the reason why is because if I have two angles, I actually have three angles. Because the third angle is 180 minus another 2. So for both triangles, if I have two triangles here, okay, if I have one triangle here, and I know that they have the same, the angles correspond, the corresponding angles are, two of them are equal. Okay, then I know that the third one is also equal because they must add up to 180. So two of them, and the third one must be equal. Make sense? Good. Now, if that's the case, it still doesn't mean they're the same size. that was this problem here. There could be two different sizes. But if I have one side length that is equal, then all the other three side lengths must be equal, because now I've determined they are the same size. At least one side length is the same, all of the angles are the same, so all of the opposites, all of the other sides must be the same as well. And that's actually easy to prove, because if I go and draw two triangles, so let's say I've got this triangle, and I draw the second one on top of this one, okay? So let's say I draw the second one on top of it. They must always fit. At least one of the angles must fit on the other angles, is it? Because all your angles are the same. So now, let's say we did draw them like that. Now notice that the only way to draw this so that one of the angles, one of the side lengths are equal, because now all of the side lengths are different lengths. The only way to draw this then so that all of the side lengths, one of the side lengths are equal, is to draw it so that all of the side lengths are equal. You understand? So if two sides are equal, then two angles are equal, then all three angles are equal, and therefore, and if there's one side that's then also equal, all of the sides will be equal. Make sense? Good. And it actually follows from the sine rule as well, because sine A over A is equal to sine B over B. I should actually do it this way around. Sorry. When you work with the sides, start with your side on the top. Okay. So let's say I know side B, and I know all the angles. In other words, I can get A is equal to B over B times sine A over sine B. So when you work out the one side length, notice that the other side length depends on the side that you know and the angles that you also know. Okay. So if one side length is equal, then all the other side lengths will also come down to the same thing. I might have confused you there, don't worry. But so here's our three congruency principles: side, 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 angle, side, and side, angle, angle. Doesn't matter. This last one, order doesn't matter. The first one. Then there's another one, and it comes to the 90 degree. When you're specifically working with 90 degrees, if you work with 90 degrees and you have these two sides, so you've got two triangles. Remember, the whole time I'm talking actually about two triangles, and you know that the corresponding, this is side, angle, side, because you've got side and the interior angle. We already know that. But the 90 degree theorem or the 90 degree is a special case of this top one, that if you have the hypotenuse and any side, then for two, so for example,
so is that like Pythagoras in a way?
It is because of Pythagoras. Because if I have an hypotenuse and another side, then this one, according to Pythagoras, will have, so if this side length is say this is A, that is R, yeah, let's do that. Let's call this one C, that one A. Then I know this one's also C because they're equal. And then this one is also A because they're equal. So in both of these two, this one's side length will be C squared minus A squared. C squared minus A squared. So both of them will get the same third side, and that's what I want. But notice it's not side, angle, side, because I didn't have this to begin with. I'm given the hypotenuse and another side. Now in this case it's a special case where the third side is given by formula. So if I have any two sides, the third one, any two sides in a third, in a Pythagorean triangle or a 90 degree triangle, the third one must then be given by the same formula. Okay, so that is now a special case. So that one will say it's the 90 degree side, side. Or you can say, 90-degree hypotenuse and side. Okay. If it's not the hypotenuse, it's actually that one. Okay. Because the hypotenuse is the one that's opposite. So if you have a 90-degree triangle, they've given you an angle, actually. So if they don't give you the hypotenuse, it means they've given you the two sides that make the 90-degree, and that's why you have that one. So you wouldn't say S 90. If you did, it's not wrong. You've still shown sine 90 degrees. So. But yeah, this is special case of that. Okay, they are important. The only reason why I'm giving that is because they're now important when we get to the grade 11 theorems. Grade 11 theorems are all about circles. And the first thing we then have to do is define what is a circle. Like, how would you define a circle?
360 degrees.
Yeah.
It's what?
360 degrees.
Is that your definition of a circle? It's 360 degrees. A circle, so remember, a circle in essence is a collection of points.
All points add up to 360.
Sorry?
All points add up to 360.
The points add up to 360. How do you add up two points?
No, okay, no, the angles in a circle, I don't know. But
Here's the definition of a circle. The definition of a circle are, they're all points that have the same distance from the center. So in other words, if in geometry, that's exactly, in analytical geometry, that's exactly the formula. Because the distance formula is d squared is equal to x minus x1 squared plus y minus y1, sorry, without the square root, because I'm saying d squared. Okay, so in this case, we're just making that d is a constant. We're saying d is equal to the radius, and as a result, we've defined now x and y represent points. But okay, we're not in analytic geometry, we're in Euclidean. So in Euclidean geometry, a circle is defined as that if you connect the center of the circle with any point on the circumference, there. Actually, what's the technical word that I should use? Is AB equal to B to AC? No, technically it's congruent. It's not the same line. Okay, it's okay. If you said equal, it's not wrong. I'm just trying to get you into the right.
You said equal radius. Okay. Equal radius.
Okay, so why are they equal?
Because they're from the same point in the circle center.
They're equal because it's the definition. It's what a circle is it's a point that has the same distance from the circle than any other point in that circle. So yes, they say equal radii. Okay, that's not really the reason they're equal radii. They're actually points on the same circle. Points on the same circle. Because that's why they're true. They're true because that is what a circle is. It's what we define it. It's the same as 360. You don't have to prove something is 360. You define a revolution is 360. So why would AB be equal to AC? Because B and C, basically because A is the center and B and C are points on the circle. So they have to be equal because of the way we define a circle. Okay. Now, let me just quickly remember the law, the order of. Okay, yes. So now we're going to look at some of the theorems. One of the theorems, the circle theorems, is that if we had a circle, and from the center of that circle, if we had if I connect any 2 points on a circle, it's called a chord. A chord is a segment between any 2 points on a circle. Okay, so any 2 points connect to a chord. If I now take a line from the center of the circle and I cut the segment, sorry, not the segment, the chord at a 90-degree angle, the theorem says that I will also halve the chord. So the shorthand for this is is it line from center to midpoint? Line from center parallel to chord. Okay, so line from, I thought there's something shorter than line from center perpendicular, sorry, not parallel, perpendicular to chord. Okay, that's the shorthand you would use. And so if we, and now we get to the theorems that you guys have to know. And they're not difficult, I promise you. None of them, except for the great cloud theorems, are difficult. The rest are not difficult. They're easy marks, but they're difficult to go and study if you don't think in this reasoning way. Okay, to go and study them off by heart, it's probably 5 pages of theorems. I mean, but in the end, all you need to know really is that what you're trying to prove, and I shouldn't have drawn these two. That's what I'm trying to prove. So your construction here would be to make 2 triangles. So if this is circle OAB, then I'm going to construct OA and OB. So do you notice how I made 2 triangles? Okay, and notice how in this triangle, what information do I have in these triangles? Now I want these 2 triangles to be not equal. The word is congruent. If I can show they're congruent, in other words, this is the point M where they cut. If I can show that OMA is congruent to OMB, then I know MA must be equal to MB. If MA is equal to MB, then I've shown. Okay, so that's the proof. Okay, so construct OB and OA. There's my first mark. And now, what can you tell me about those 2 triangles? So you'll start, when you do congruence, you say in triangle OMA and now you follow the same order, triangle OMB. What can you tell me?
OA is equal to OB.
OA is equal to OB. Okay, and you can say equal radii. That's fine. Equal radii. Easiest way to write that. What else can you tell me?
OM is it's common.
OM. These 2 are actually congruent because they're not the same line. Again, if you say equal, it's not wrong, but this is literally true. OM is equal to OM. You don't even have to give a reason, but that's fine. Common side. Okay. So again, in congruency, I want to prove either that 3 sides are equal, but I can't prove that 3 sides are equal because that's what I want to actually conclude.
M1 and M2.
Good, so let's number them then. Okay, so or rather it's probably best if you say OMA and OMB. Okay, angle OMA is equal to angle OMB. Okay, that's given. I gave you that it's perpendicular. If they say it's perpendicular, perpendicular means I cut it so that on a straight line the 2 sides are equal. Okay, given, and therefore triangle OMA is congruent to angle OMB. Why? What's the reason? So I've got one of 3 to choose from, either side, angle, side. or a side and two angle, or 90 degrees hypotenuse and side.
Could be two. Side angle, side, or 90 degrees hypotenuse.
No, if you say side angle side, then you must look at the angle and the two sides. So notice we did side, side, and angle. That's fine. But then the angle must be between the two sides. If you use that one.
Oh, then it's not. It's 90 degrees.
It's the 90 degrees hypotenuse. So in other words, you'll look at your if you use this opposite side in your proof, then you know it's 90 degrees hypotenuse side. Okay. Cool. And now we conclude. Therefore, AM is equal to BM, and then your reason is from congruence. Okay. There we've proven our first theorem. The line drawn from the center of a circle perpendicular to a chord bisects the chord. Okay? Not difficult, huh? Possible. Maybe only 4 marks for that one. 3 for the congruence, 1 for the proof, 2 for the congruence, and 1 for the conclusion. Or maybe if you're lucky 5, then it's really an easy 5 marks. Okay. Next, the angle subtended. Okay, so let's. There's then another theorem that's just the converse of this, which is and you don't need to know the proof, but you need to know the theorem. So the other one is if I then go from the center of the circle to the center of the chord, then I know I'm cutting at 90 degrees. So that's what we call converse theorem. So it's the theorem that is just applied in a backwards direction. Does that make sense? It's not always true that the converse is not necessarily true. For example, if it rains, then it's wet. Would you agree? If it's wet, did it rain? No. Okay, so that's the converse. So if then is true, going from backwards isn't always true. Now, if it rained, then it's wet. If it's wet, it might have rained. But it's not true that it definitely rained. But if it rained, it's definitely wet. Do you understand that? Now, the contrapositive is true. Contrapositive means that I take it from backwards, but in the negative. If it rains, then it's wet. If it is not wet, then definitely did not rain. Do you understand the contrapositive? It's taking the backwards, but in the negative. That's also true. If the if then is true, then the contrapositive, taking the negative from the back, that's also true. Okay, so if I go from the center of the circle perpendicular to the chord, then I bisect the chord. It doesn't then just necessarily follow that if I bisect the chord, I've gone from the center perpendicularly. But so in other words, it's a new theorem, it's a different theorem, and it also needs to be proved. It's proved in exactly the same way. Exactly the same way. The only difference is now we're not given this. We're given that these are equal. So now when I do my proof, I'm doing the same things, except now instead of saying that the angles are equal, I'm saying that the sides are equal. And now I have side, side, side. So I've got two triangles that are congruent, but that means that M1 is equal to M2, and M1 plus M2 is equal to 180 degrees. Therefore, M1 is equal to 90 degrees. M1 is equal to M2 equal to 90 degrees. You see, similar, but if I don't prove it, I can't just assume it because I'm not using the contrapositive. I'm using the positive from the back, and that's not always just true. Okay, another theorem. Would be just want to see if that's the one that's up next. Angle subtended by an arc at the center is double the angle. I figured this one, guys. We know this proof. This proof forms the foundation of all of the other circle proofs. Okay, so these these line from center perpendicular to chord, they're a different type of circle geometry, but now we get to angles on the arc and angles at the center. That's a little bit different. So an angle at the center is when I make from the center, I draw two lines. The angle at the center is that angle that I make, that these two radii make. The two radii I want to draw. Okay, you get that? Makes sense? An angle on the arc is that, especially in this case, and where this theorem applies, is when I go from the center to the arc, if from those same 2 points I make an angle somewhere on the arc, anywhere on the arc really, doesn't really matter where I make it. So let's just make it simple for now. Looks like a Star Trek symbol kind of. Okay. Do you notice that? Then the theorem says that this angle, if this angle is x, that one will be 2x. So the angle at the center is twice the angle on the circumference. Now, this is going to form the foundation of a lot of other proofs, and you see the other proofs are actually easy if you get this. Okay, but this one's proof is slightly complex, slightly, not difficult, but slightly. Okay, so we need to go and prove it. So I'll show you the proof, and most of the time it's just remembering what the construction is. So this one's construction, let's just name this is A, B, C, and then usually we name the center O. So what we'll do is we'll draw a construction from there through the center, and we'll extend it slightly. So what theorem do you think is going to apply here?
Exterior angle is equal to
the opposite interior. Okay, so notice now, oh, this is a proof I actually forgot. Before I get to this thing, let me quickly look at a proof I forgot. Okay, it's actually a proof we can only prove once we've done congruence, something based on congruence. Okay, it's a good reason why I maybe haven't proved it yet. Okay, if I had to a triangle, an equilateral, what is it called? Equilateral, eh? An equilateral triangle is where two sides are equal.
three sides are equal.
Isosceles triangle. Isosceles triangle. Saying thank you. Okay, so isosceles. I don't know how to spell isosceles. Okay. In an isosceles triangle, two of the sides are equal. Then the theorem says the base angles should also be equal. In other words, in an isosceles triangle, these two angles here must also be equal. That's the theorem. Now we must prove it. Okay, we'll drop a perpendicular line here. Okay, and then what will we do?
90 degrees.
So then we know this is 90 degrees. But let's quickly think of how will I going to show that these two angles are equal? What is the spirit of my proof going to be? How do you know?
How do we know that those two are equal?
Yeah.
Because 90 degrees angle, so they're all Pythagoras.
Don't all the angles add up to 180 inside the triangle? Don't all the angles in the triangle add up to 180 degrees?
Yeah, but you only have one angle in that triangle, the 90 degrees.
But you've got two sides, and one's common, and the others are equal.
So what are you going to do in these two triangles? you're going to show congruence. You're going to have A you're going to have A don't do that. B and C. You are going to construct A in perpendicular to BC. That's your construction. And again, you don't need to know these proofs, but they help you to understand the geometry. So when you have AN perpendicular to BC, now you have in triangle ABM and triangle ACM, we have AB is congruent to AC. We have AM is equal to AM. Common side. This was given. This was common side. And we have that AMB is equal to AMC. What reason did we get? Yeah. Was it given?
No.
It was construction. That's how I constructed it. And I'm allowed to construct anything I want. Okay. So by construction, now, as long as it's helpful. And now from this, what can I conclude?
That it's congruent then.
Yes, so in other words, triangle ABM is congruent to triangle ACM. And what is my reason?
90 degrees.
Well done. Because I look at the 90 degrees and then I look, did I have the hypotenuse? If I did, then it's the 90 degrees hypotenuse side. And therefore now in a congruent triangle, all angles are equal and all sides are equal. So since I know they are congruent, I know that angle B must then be congruent to angle C, or equal if you now use the word equal. It's fine. Okay. Okay, cool. We've proven that, and the reason why I wanted to prove that is because we need that fact for this. So you'll notice this is, I do admit, this is slightly complicated, but it's still not very difficult. You just need to keep track. So what can you tell me about, can you see the triangles? This is not a congruency proof, so I just don't want you to now think in that direction. We're not using congruency, but can you see the triangles that I'm going to work with? Where's the triangles?
AOB and AOC.
Triangle AOB. Okay, so let's just first work in triangle AOB. Can you see that I extended AO? Okay, so let's extend it to D, just so that I have a way of referring to the extension. Okay. So I must say construction. So in my proof, I tell them what I constructed. Construction. AO extended to B. Now I extended it because I want to work with some angle in BOC. You see? So, and I've got two triangles now, and I can see, so I've got an exterior angle for ABO, and I've got an exterior angle for ABC. You see that? Are you sure? Remember, an exterior is when I take one of the sides and I extend it. So, what can you tell me in triangle AOB?
A1 plus.
So let's call this thing 1 and then 1, 2. Yeah.
A1 plus B is equal to.
Let's call this one then 1 and 2. Okay, so you told me that A1 is equal to, sorry, Yeah, A1 plus B is equal to?
It says no.
Oh, sorry. That's good. Yes, are you honest? Yes, are you outside? Okay, I'm not needing it. Hey, hi.
Oh, there's someone outside. I think there's a problem. Can you just put in the two exams yet?
We start taking good.
Yeah, sure. It's going to be a TV. Are you ready?
Nah.
From now on, you must just cut the ladies, cut the guys, just focus. When you talk too much, be writing also. Yeah. For just a month, and then after that, sleep on it.
Okay, so the second theorem that we're going to look at is a very common one. It's very often used in our actual work. Not so much that we use the proof. They don't often ask the proof because it's fairly simple proof. But I like to think of it as a butterfly because it kind of looks like a butterfly. And the proof says that the tip of these butterfly wings are are equal angles. Okay, so these tip of the butterfly wings are equal angles, not these two opposite, okay, but the ones that are on the same side. The proof says that angles subtended by the same arc. Now what an arc is it's 2 points on a circle, all the circumference between those 2 points. That represents the arc of the angle. Sorry, the arc. And subtended means it understands. In Afrikaans, it's actually exactly that word, onderspan. It spans the underneath of it, subtend. And so you can see that these are 2 angles on the arc, and they both have this on an arc, and they both subtended by the same arc. In other words, they come from the same 2 points and they're made on the same arc. And so that's the theorem, that those angles are equal. Now, in order to prove this, once again, all I need is the construction. Once I know what the construction is, it's actually a very simple proof. Here's the construction. All I do is I construct from the center an angle at the center, because you can see that on the arc I can make infinitely many different angles, but at the center I can only make one angle. Okay, and so can you see how you can use this? How can you prove, using a theorem that we already know, to prove that these 2 angles are equal? So this is A, B, C, D, and O.
Angle at the circumference is twice, angle at center is twice the angle at the circumference.
Yeah.
So if you use the same arc BC, it means that A and C are equal, since angle at the.
Okay, so in other words, and it's now all about saying it. Now, how would you write it now? Remember before, when we wanted to show the 2 angles are equal, like correspond vertically opposite angles, we said that A1 is equal to 180 degrees minus A2. A3 is 180 degrees minus A2, and because these 2 are equal. So I got a formula. So when I want to show 2 angles are equal to each other, try and get an expression that the one is equal to, get another expression that the other one is equal to, and then those 2 expressions might be the same, and then I can show they are equal to. So you want to show that A1 is equal that A is equal to C. So A is equal to what? What can you say A is equal to? Using the theorem we just had.
Can you say that A is equal to B?
No, A is not equal to B. Huh? It's not isosceles. See, this line here is not from the center. No, not the proof, this theorem. This theorem said that the angle at the center, which I just constructed, is twice the angle on the circumference.
So is angle O equal to 2 of angle A?
Yes. So angle A is angle O divided by 2. And angle C is angle O divided by 2. Therefore, angle A is equal to angle C. How simple that proof is, using an established proof. So this is this one you'll say angle at center equal 2 times angle at circumference or arc. Okay, and same here. We'll just give that reason. Okay, very common theorem to ask. Yeah, so you'll notice that what it is you find a triangle in a circle. That's the first notice, and a tangent at one of the vertices. Okay. Now, for some reason, people do exterior angle of a quadrilateral. I don't know, but in the end, all it is that the angle made between this tangent point at that tangent point and the angle in the opposite segment. So a segment is when you take a circle and you cut it anyway. Then each part of that is called a segment. So you'll see this angle is made in this segment, and then the triangle's angle in the opposite segment would be that one there. These two would be equal in size, and then they always come in pairs. So there must be one on this side as well, because there should be one here. Okay, and that one will be equal to that angle on the opposite side. Okay. Different ways of proving this. I'll show you the one I think is the easiest. You could prove it using and that's the way I originally did it. I didn't go and look up any of these proofs in the textbook. I really thought them all up myself, and if I go look at the textbook, it's the same that the textbook do. There's no, but this one actually had a different way that I originally did it, and then I went to look at how. Actually, I was writing a memo, and then I couldn't remember the proof I used, so I came up with a different one, and I ended up seeing that this is actually the one that they use in the textbooks because it's a little bit simpler. This one says you draw your construction from that point through the center, and then now it depends which one are you proving. So let's say this is D1. That you want to prove is equal to B is equal to A. So you want to prove that D1 is equal to A. Then you draw it from D through the center. You make a new point. Let's just call that F on the center, and then from there you draw another. You connect it to the angle that you want to prove. Okay, and so can you see some of the theorems that I'm going to use? Some of the theorems that I'm going to use. There's two theorems that's going to form the foundation of this. Which are those two theorems? Sorry?
Angle at center.
The angle at the center, it's more an angle in semicircle, because I now know that one must be 90 degrees because I've got a diameter and an angle made with diameter. What else have I just done by drawing this construction?
The butterfly.
You have, but you'll notice that, yeah, why not? You're right. The butterfly thing. This angle, I don't even know if that was the original one I was going to use. It's equal to that angle. Notice, and what else?
That D is 90 degrees.
D is 90 degrees. And those are the three formulas that or the three theorems that's now going to form them. And that's why they like to use it, because it uses all three of those important theorems. So, so first of all, you would show that A is equal, this big A, so we'll number this 1 and 2. So A1 and 2 is equal to D1 and 2, both of them are 90 degrees. And then let's see then A2 is equal to D2, so A1 must be equal to D1. Okay, so first we show that they are equal, both 90 degrees. So I'll say, okay, A1 plus A2 is equal to 90 degrees, angle in semicircle. then d1 plus d2 is equal to 90 degrees, radius perpendicular to tangent, or tangent perpendicular to radius, however you put it. Therefore, A1 plus A2 is equal to D1 plus D2. Make sense? And then I say, but A2 is equal to D2. Do you see the butterfly? Can you guys see that?
Yes.
So A2 is equal to D2, angles, what's it, angles in, angle, what? Let's go look at that. Lines of the equal chords. Lines of the 6 things, angle 2 points, 4 points up, whatever that is.
Is it angles in same segment?
Angles in same segment. Angles of thin, yeah, angles in same segment. Okay, so angles in same segment. Okay, so you see there's the segment, the part of the circle, and there's two angles that's made in that same segment. Okay, they have to start from the same point again. So angles in same segment. So if A is equal to D, then then that must mean that A1 is equal to D1. Make sense? You guys happy with that? Very, very often asked. The way that I proved it was to actually draw. The first time I did it was to draw this angle at center, and then what happens is, because these are equal, so let's say this one is x and that one is x, and this one is 180 minus x, so then this angle in here, sorry, this one is 180 minus 2x, so this one becomes 90 degrees minus 1x, because it's just half of that. And then this one is, because you've got the 90 degree coming down there, and you have that one is x, and this one is 90 degrees minus x. Because, so I just named, so it's also an easy one. It's not a bad one, but I like this one more. It uses more of the theorems. So, but looking at it now, it seems like somewhat simpler. Okay, but you just use that x. This one just, you use the extra fact that the angles are the isosceles triangle there. So it uses an extra proof there. Okay, then there's one other one. I'm not even going to look at it. I'll just show you the theorem. The theorem just says that if I have one tangent line from here and another tangent line at there touching, then these two lines. Can you see the yellow?
Not too
bad. Okay. But, oh. Okay, if I have two tangent lines, then these lines are from the same point, but they have opposite, they touch on different parts. Then the two tangent points are, the two tangent lines are equal. It's actually a very easy proof. You just connect them, and you connect the center. No, I lie. You don't connect the center. You connect both of them with the center. So you connect both of them with the center, and then you connect the center with the outside point. And we know that that's 90 degrees and that's 90 degrees. Okay, they've got a common side, and the in and radius, yeah, radius. So we don't have the hypotenuse. So it's not the, so it's the, no, we do have the hypotenuse, sorry, yeah. That's the common side. The hypotenuse is a common side. So we've got the hypotenuse and one other side which is sufficient to show congruence, and then those are equal. So it's a very easy proof, so it's unlikely that they will ask it. Okay, so let's quickly see if we've looked at all the, we've looked at much more than we needed to, but just because I think it really explains, helps you to get the spirit of what geometry is about. So we've done the line drawn from the center, bisects the chord. The angle subtended by an arc at the center is double the size of the angle. Okay, that was that. The angle at the center is double the angle of the chord. The angles opposite of a cyclic quadrilateral are supplementary. The angles between the tangent to a circle drawn from the point of contact is equal to the angle in the alternate segment. That was the one I just did before. And then these are the two grade 12 proofs that you have to know. Okay, so I'm not going to get to them today, but I'll get to them tomorrow, hopefully, and put them online. But both of those proofs are online. You guys will really get it. Although those are two very difficult proofs, I must admit. If there's any difficult proofs, it's those two. But if you just, most proofs, if you get the construction, you've got the trick, and you just follow it on from there. Cool. I think what I'll do is I'll look at, with the time remaining, at the exam paper, and you'll see that in grade 12 they often mix the grade 11 and 12 work now as well. So this question 9 is a mixture of, whenever it's similarity, it's usually grade 12 work, but whenever it's circles, it's grade 11 work. So they've mixed it too. So if I had to prove that something is similar, remember what we said, congruent means sides are the same, similar means the angles are the same. So if I had to prove that triangle ABC is congruent to CDY, all they're really asking me is to prove that A is equal to C, that B is equal to D, and that C is equal to Y, which isn't grade 12 work. It's grade 11 work because it's a circle. Then they go over, and now I have to prove some sort of multiplying relationship between the side lengths of some triangle or what, some side. And that is usually the grade 12 work. So let's go and do this first one, even though we've not looked at similarity at all. All it's asking me is to prove that A is equal to C, B is equal to D, and C is equal to Y. Is that okay? So I'll show you the triangle just now. So they're asking me to prove that triangle ABC is similar, that's how we write similar, to triangle CDY. So they want me to show that A, B, C, so this A, let me mark it with a color. Color would usually be helpful when you do trig. CDY must be equal to C. Okay. B is equal to D, and Y is equal to C. So Y is equal to C. Now, if I had to prove this, I'd only need to prove two of it. The third one would follow because of the interior angles of the triangle adding up to 180. Okay, so which one do you guys think is the easiest? Which one can you almost immediately show?
The green. Okay. No.
Sorry? Pink one. Okay. So why is D2 equal to B2?
Tangent chord.
No, this is not a tangent.
Radius and no, it's not.
It's
It's a
two.
chord. So,
Remember, we had a theorem that says if we have a cyclic quadrilateral, if we extend one of the sides, it's equal to the opposite interior. Okay, so there is one mark, the easiest mark to get. Okay. However, now for this one, and my suggestion is really that you look for your tangent lines, and then look for as many triangles as you can that this one is equal to. So for example, this green one, so let's call it x. It's usually helpful to just give something a value. So let's call this one x. That one was not easy to find. What is C4 equal to? I'm teaching you very poor geometry skills. You have to just read your, because you might know that BC is equal to CD. If you know that they are true, then that theorem that angles subtended by the same arc are equal. It's also true that if the chord was the same length, then the opposite angles would be the same. Okay, if they had the same length. So if you knew that BC and CD was equal, you knew A1 and A2 would be equal. You don't know that, but look what you do know. They say ABC is a cyclic quadrilateral, AC bisects A, which means A1 is equal to A2. So AC bisects A. So in other words, you already know that A1, if this one is x, that one is also x. And we already know that this one is equal to that one because of the...
And you use the tan chord theorem.
There's the tan chord theorem. So C4 is equal to A2, tan chord theorem. You can also write it like that, tan chord theorem. But A2 is equal to A1 given, because they say it's bisected. Therefore, C4 is equal to A1. And next, now you can just say, now I think it's silly that you have to say it, but for me it follows so trivially that the third angle must be equal, but okay, we won't do that. The third one, you'll just now show that angle Y is equal to D2 180 degrees minus D2 minus C4, and angle C2 is equal to 180 degrees minus B2 minus A1, but B2 and A1, B2 is equal to D2, A1 is equal to C4, therefore Y is equal to C2.
7 marks.
7 marks, that's not bad, huh? So this was really, initially I thought it was a difficult paper, but when I looked at it a second time, I'm withdrawing that I think it's difficult. I just think people didn't know their theorems. Okay, so here, and eventually you say, therefore, you get a mark for this, therefore, triangle ABC is similar to triangle CDY. And remember, it must be in the same order, and then just say angle, angle, angle. You have to say angle, angle, angle. Okay. Another thing that will make something similar is, remember we had, no, let me skip that. Okay, let's go on. The next one, the next question would be based on grade 12 theory. and so I'm not going to look at that now. But it follows directly that when two things are similar, that there's a proportional relationship, and you then just manipulate that relationship in some other 5 marks, but I'm not going to go into that, to get to the expression that they want. But you start from what you've just, usually you would start from what you've just proven. If it's something like this, and in the previous question they asked you to prove similarity. I'm not exactly sure, but if it's an AC squared, you can almost be sure it's going to be AC over one of those is equal to the one that's left divided by AC. So they cross-multiplied to get this expression. And you will look at that expression to find the triangles that they are actually referring to. Okay. The next question, I'll copy it just now, but let's just read the question. O is the center of the circle with K and N points on the circumference. KL is a tangent to the circle. M is a midpoint. Let me just see what the question is. Similarity, yeah. It's still grade 12 stuff, but you use all your grade 11 theorems. Okay, M is the midpoint. Okay, of the chord K and OL intersects at P. Okay, so everything that they're saying here is indicated on the graph. The reason why I read that first is just to see, like in this one, they didn't show me here that A1 and A2 is equal. So that's why we just read there to make sure that all the information they give me is actually recorded on the sketch. And they're asking me to prove that that is similar to those. So again, it's just going to come down to proving that KOM is similar to triangle KLM is similar to triangle LOK. Okay, which just means I must show that angle KOM, so there's KOM, so I must show that K1 is equal to KLM, so K L in that can't be right. Yeah, this is wrong around. K, do I have it correct there? KOM, KLM, K. This one should be LKM. LKM, that's a mistake. Okay, so this angle must be equal to that angle, and is equal to itself, so that's fine. Then O must be equal to LKM, so it's LKM, so those two angles must be equal. And so O equal to K2 and O again, yeah, that's fine. And then finally that M, KOM, so KOM, so it's the 90 degrees, so this angle is LKM is equal to that angle, and that's equal to this angle combined. Okay, you guys think you can do that? Okay, let's start. Which one do you think is easiest to prove?
M1 is equal to...
Sorry?
M1 and M2.
Is equal to M2?
Yeah.
I think so too. But why?
It's a line drawn from the center.
Well done. So first, so that's what I'll have to say. I have to say OM is perpendicular to KM. And then line from center of circle to center of chord. Okay? So in other words, it would follow that n1 is equal to n2. Okay?
O to K, that's perpendicular.
Well done. So OK is perpendicular to KL. That's the radius perpendicular to tangent. Okay, therefore this OKL is also equal to N1, which is equal to N2. Right? So I've shown that.
Okay. So if we already have two angles, it means that automatically
The third angle is, no, you don't even get a mark for that third angle in this one. So this one is, it's not tricky, it's actually a very common thing that happens when you work with 90-degree triangles, is that notice how in LOK, okay, how in LOK and LKM we already have a common sign, which means in triangle LOK and triangle LKM we already have a common we've already shown that, but now we've also shown that we also know that L is equal to L. Therefore it follows that now I've got 2. Therefore it follows that K2 is equal to O. You see? That last one now follows, and now so K2 is equal to angle O. So triangle LOK is similar to triangle LKM, and now I already have that in the other one. We already, so in KOM I now also have that O is equal to K2. So now I already have that O is equal to K2. K2 is equal to O given. The reason you would give here why this is true is because angles, angle in triangle add to 180 degrees. That's why this one follows kind of normally, but you don't even get the marks with steps in between. So this is K2, you'll just say already shown. Okay, so K2 is equal to, K2 is equal to O. Then we've already shown that M is equal to K. So M is equal to K, already shown. And then L is equal to L, already shown. So, well, common. Okay, and so they're also similar. Wait, I've just done this one again. Sorry, I'm supposed to do the other one. Okay, I'm supposed to do KOM. Okay, in KON and which one? LKN, because that's, and LKN. I've shown just now, so still KO and LK, and I've shown that N is equal to N, that's the perpendicular angle, and then the third one follows. Okay. So again, it's not difficult, but it often happens when you have these 90-degree triangles that that because you have, actually what you have here is you've got three 90-degree triangles. You've got 1, 2, 3. And if you can just show that 2 of those angles are equal, other than the 90 degrees, then all of the other angles work out necessarily because of the fact that they add up to 180. Okay. So this is a very common, this method of drawing a 90-degree triangle out of the 90-degree triangle on top of the hypotenuse is very common. You can actually go and look at past papers, you very often get it, that they have a 90-degree triangle, or out of the 90-degree angle, they draw a 90-degree angle on top of something else. This is just a very clever way of actually doing it in a circle where you first have to get that information. So much so that there's actually a theorem that says that if you draw a 90-degree triangle, then a 90-degree angle on the hypotenuse through the other vertex, or if you drop a 90-degree triangle out of the 90-degree triangle on top of the hypotenuse, that the triangles created are all similar. And so that's why this proof is only worth 6 marks, because all you had to show was that this was 90 degrees and that was 90 degrees, and then you apply this other theorem, but I don't teach it. Okay, the rest of this, okay, let's look at this question maybe. The exterior angle of a cyclic quadrilateral is
equal to the opposite interior.
Yes. And here they give you a triangle. I just don't have enough time to maybe go through actually doing the steps with you, but I want to show you just what we actually call problem solving. So we know that the angles, the opposite interior angles of a cyclic quadrilateral add up to 180. We know that the exterior angle of a cyclic quadrilateral is equal to the opposite interior. Okay, we know that if we have a cyclic quadrilateral, that there's certain theorems that we can apply. But now often, and this is usually classified as problem-solving questions, and by that we mean it's the most difficult of the, not difficult, but thought-intensive, is to apply the opposite. So instead of giving you a cyclic quadrilateral, they ask you to prove that something is. And so either then you have to prove that the opposite interior angles add up to 180 and therefore they are, or you have to prove the exterior angle is equal to, or remember the butterfly thing? If you can prove that in a butterfly, in that butterfly, for example, and that's what they're asking here, PVTR is cyclic quadrilateral. So prove that PVTR, but notice PVTR has that butterfly. So if you can prove that P3 is equal to V2, then PVTR must be cyclic quadrilateral. Do you understand? So you're proving the opposite. You're not assuming it is a cyclic quadrilateral, but you're proving it. In this case, they just give us a bit of information. In the figure below, QS is at a diameter. Now, once you know that's a diameter, you immediately look for what? Angle and semicircle. So you immediately know that P1, 2, and 3 is 90 degrees. Okay? And you already know that R1, 2, and 3 is, R1 and 2 is 90 degrees. So that's helpful. Is it? Yeah. Because there it immediately follows that in your first question, prove that PVTR is a cyclic quadrilateral. Because we know that P1, 2, and 3 is 90, then P4 is 90. And if you know that R1 and 2 is 90, then R3 is 90. So R3 is equal to P4, and do you see that strange looking butterfly there? Wide wing? The tips of the butterfly is in, and that is PV2R. And that was it. Okay. Then prove that OP is tangent. Can you again see? Usually they tell us it's a tangent. Now we must prove that OP is tangent. So tangent to what? To the circle through PVTR. So we know PVTR is now a circle. We can draw a circle through those. Now they want me to show that OP is a tangent to that circle. Now what tangent formula apply? What tangent theorem?
Can't use the term chord theorem.
The term chord is where the angle between the tangent. So in other words, we need to find, here's the tangent. What would be a chord in this imaginary PVTR? So here's the circle, PV2R is now imaginary there. Because they ask me, prove that OP is tangent to PVTR. PVTR. So give me, here's the tangent line. Give me an angle between just give me a chord.
Okay, can I use PR?
PR is a chord. What would be the angle in the opposite? So here's P2. There's the chord. Where is the angle in the opposite?
Wouldn't it be R1?
R1. No, here's the. You're not. I don't think you're seeing the circle. So let me copy it. So I'm going to be able to draw the circle. Similar. I don't know how I just did that. That looks. Okay, there we go. So maybe taking in a compass would be helpful because now. Oh no! Oh, no. Anyway. Is roughly a circle. So now I must prove that that OP is a tangent, and he just said, okay, well, let's use the chord PR. If PR is the chord, what is the angle in the opposite segment? Sorry?
Would it be 90 degrees?
I can't hear?
Wouldn't it be 90 degrees?
No, if this is the... So here's the tangent. The 90 degrees got to do if I had something from the center. This is the tangent, and here's the angle between a chord. There's a chord. My question is, what would P2 equal to? What is the angle that's opposite? So in other words, you must find the triangle that PR makes.
Can you say T2, T1?
T1, yeah. It makes a triangle there, T1. but it also makes a triangle B. Okay, so this is what I want to prove. I would want to prove that either P2 is equal to T1 or that it's equal to V1. Then I would have proven it. To be honest, I can't remember how this proof works. Well, I know these two are equal. Equal to this angle. So this is an angle at the center. So if this is x, let's say that one is 2x, then that one here is x, and this one here is x. I think that's helpful. So here is 90 degrees. Two is equal to there.
R2 is also equal to T2.
R2 is equal to T2. And then S2 is 180 degrees minus 2x minus 90 degrees. Oh no, this is also just 90 degrees minus x. It doesn't look helpful yet. I want to show with this one. Then we have that this one I have that OPS, this OPS, yeah, okay, let's go for OPT. That angle OPT is equal to 90 degrees minus x. So because this one is x, that one is x, because these are radii. Okay, and then this one we said was 90 degrees, and then so this part is 90 degrees minus that x. Now if I can then just show that this is the tangent, this is the chord, that's the tangent. If I can show that, and this is the triangle, that this is also 90 degrees minus x, then I've shown it. Okay, then I have that this angle here is equal to that, so this is y, so that one is y, this angle here, and this one is y, because these are that butterfly and these are those butterflies. You see that? Sorry, it's getting a bit messy here. Then this angle here is the exterior angle. Guys, I'm running out of time. I need to leave in 5 minutes.